Let's look at the length of a fractal. A fractal, again, is a shape that shows detail at every level of magnification, especially a shape that is self-similar. In other words, parts of the shape are similar in shape to the whole. A famous example of a fractal we've seen before is the Koch curve, developed by the Swedish mathematician Helge von Koch in the early 20th century. Start with a line segment of length 1, draw an equilateral triangle on the middle third of that line, and then erase the bottom edge of the triangle. And we repeat the process on the remaining segments. So for example, what we would do here, so again, just repeat the process. So draw an equilateral triangle in this segment, equilateral triangle in the middle third of this segment, kind of sloppy here, sorry. Equilateral triangle on the middle third of this segment, equilateral triangle in the middle third of this segment, and then we just erase the bottom edge of each of these triangles. There we have that. We erase the bottom edge, we get something like that. And then we just repeat the process ad infinitum. So again, for this next one, so again, what we do is, draw an equilateral triangle here, equilateral triangle here, equilateral triangle here, equilateral triangle here, erase the bottom edges, and we get this over here. Whoops, sorry. And we get this over here, and erase, and then we continue the process again. We end up with this, continue the process, do the process again on each of the remaining edges. We end up with something like that. And the ultimate Koch curve will look something like this. Now my question is, assuming that the original segment has length 1, what is the length of the Koch curve? Well, the original segment has length 1. So what's the length? What's the length of this segment here? What is this length? What's the length of this next stage? Well, this segment has length 1/3, and again, that's because the original one had length 1, and since this is each of these is a third over here, you've got a third, third, a third. Notice that this we know is a third, this we know is a third. Gosh, why is each of these a third? Why is that? Well, this is an equilateral triangle, and in an equilateral triangle, the edges have the same length. We know that this is the middle third, so this and this must have the same length as the bottom edge. So this is a third, a third, a third, a third. In other words, the length of the Koch curve at this stage is 4/3. So notice that in going from here to here, we multiply the length of the curve by 4/3. Ditto with going from here. So at each stage, the length is multiplied by 4/3. Ditto in going from this stage over here to this stage over here. You're multiplying it by 4/3 for the same reason, because this segment over here, this part, is 4/3 as long as this part was, and this part is 4/3 as long as this part was. So basically, this whole curve over here at this next stage is going to be 4/3 the length of the curve at this stage. So the length of this curve is 4/3 times 4/3, in other words, 4/3 squared. In the same way, this will have length 4/3 cubed. This has length 4/3 to the 4th, and this has length 4/3 to the 5th. So what's the length of the ultimate Koch curve? Again, this is not stage 6 or stage 7. This is stage infinity. The length is going to be 4/3 times 4/3 times 4/3 times 4/3 times 4/3 times 4/3, etc., which is infinity, because each of these numbers, they're all 1.333, etc. You multiply them all together. They're each bigger than 1. And so when you multiply them all together, since they're infinitely many, the answer is infinity. Are there any applications or implications of this, the fact that the Koch curve has length infinity? Well, this leads to what's called the Coastline Paradox. Sometimes lengths and distances are well defined. For instance, the distance from the Earth to the Sun is about 93 million miles. It doesn't really matter how you measure it. It's going to be roughly 93 million. But sometimes lengths and distances are not well defined. For instance, what is the length of the British coastline? Believe it or not, it depends on the length of the measuring stick. So in that sense, it's not like measuring the distance from the Earth to the Sun. If you have a 60-mile-long measuring stick, the coastline will be about 1,700 miles. If, on the other hand, you use a shorter measuring stick, say a 30-mile-long measuring stick, now the coastline is 2,100 miles. And again, that's because you've got finer detail. And so it's like, basically, in going from this stage to this stage, it's like going from one stage of the Koch curve to the next stage. You would get a larger answer if you used a 1-mile-long measuring stick. and an even larger answer if you used a large yardstick. Again, it's like going from one stage of the Koch curve to the next stage. The shorter the yardstick, the shorter the measuring stick, the longer the coastline.